This particular test is going to involve making a measurement of the human Stapedius reflex. These are some of the ear tips we're going to be using. If you would turn them inside out, they would look something like this. And you can see with the one on the right that there is a little module that has a membrane in it, which is associated with our new development. In the Stapedius reflex measurement that we're going to make, we're going to insert a small probe microphone into my ear canal, followed by sealing the canal with this particular construction. This will allow sounds to be created in the canal and the resulting sound pressures to be measured. To give you a bit more insight, that small microphone has been placed in this holder, and this device I have here in my left hand could represent the trapped volume. So the microphone would be in the trapped volume, and then the earpiece would fit over the end and seal tightly. So the volume you see between these two would represent the trapped volume in the ear canal. Now, for demonstration purposes, I've added a small ring here so that I can connect the receiver to this trapped volume and talk a bit about how the Stapedius reflex measurement is made. The idea is to create a sound pressure disturbance that causes the Stapedius muscle to retract and tend to immobilize the vesicular chain, thus stiffening the tympanic membrane. Under those conditions, the effective volume that's trapped between the receiver and the tympanic membrane is made a bit smaller, because now the tympanic membrane is not as compliant. If we have a probe signal in the volume while this is all happening, and it's being driven from a constant source here, we will find that the SPL in the volume changes along with the compliance of the tympanic membrane, so that a Stapedius reflex stiffening the tympanic membrane would cause the sound pressure level in this volume to increase. Here we see the electrical setup that's going to be used to create our test signal and detector for the Stapedius measurement. Detection of the volume change will come from a tone that's being played by this device, which is at about 230 Hertz, and as the volume level changes within the trapped volume, we'll be able to make that determination. This will play the excitation signal designed to stimulate the Stapedius reflex. It has about a 1-minute selection of a Peter Gabriel song that's been recorded at various levels. We start with a maximum level we'll call 0 dB, and then in 2 dB steps all the way on down to minus 20 dB. These two signals are combined in this small mixer, which in turn drives the receiver under test. Prior to testing, it's advisable to use a volume such as this, which we could call a dead ear, to confirm that our probe signal that's used to test the volume and our excitation signal that's used to excite the Stapedius reflex, that these two signals do not interact with each other. And we'll be looking at that now. There you can see we're looking at the spectrum analysis, and I start the excitation signal. You can see that there's a hole in the spectrum somewhere in the 200 Hertz range, and now I can bring up the probe tone, which you can see there. So the idea here is to make sure that the excitation signal does not leak into that hole in the spectrum in any significant way, so that the probe signal can accurately measure any change in volume. I'm going to turn on the stimulus, which will give a measured SPL in the dead ear of about 114 dB SPL. And there you see the the spectrum come up, but there's very little change, a few tenths of a dB at most, coming from the reference tone. So this would represent about as high as I think we could go in terms of simulated SPL.